Now that we have looked at how polar coordinates are defined, we're going to take a little bit of time to look at how polar and Cartesian coordinates are related to one another. And we have this series of equations here that if we want to go from polar to Cartesian coordinates, we'll make use of the first two. And the x-coordinate is equal to r cosine theta. The y-coordinate is r sine theta. And then these second two equations are going to help when we're going the other way. We're going from Cartesian to polar. And we're given that r squared is equal to x squared plus y squared. And you could rewrite this as r equals the square root of x squared plus y squared. Ooh, that's supposed to be an equals. Let's try that one more time. And we're going to actually use this little bit of information in this example down here at the bottom. And then the last one says that tangent theta is y over x. You could also think of this, and I'll do it up here, as theta is equal to inverse tangent of y over x. And we will make use of that as well. But these second two we'll use more in the second example. For the first example here, though, we're given 4 polar coordinates and asked to find the corresponding Cartesian coordinates for them. So in these 4 polar coordinates, the first coordinate is the r value, and the second one is our theta value. So going through these, let me start with 3, 0. To write this as a Cartesian coordinate, the x value is r cosine theta, so we'd have 3 times the cosine of 0. And the y value is r sine theta, so in this case 3 sine 0. Cosine 0 is 1, sine 0 is 0, so we have 3 times 1, which is 3, and then 3 times 0, which is 0. So it's going to be the Cartesian coordinate 3, 0. So in this case, they look identical. I'm going to repeat the process for negative 3, 0. So this time we'll have negative 3 cosine 0, and then negative 3 sine 0. And it's going to work in the same way. Cosine 0 is still 1, sine 0 is still 0, so we end up with negative 3, 0 again. Now, most of the time, our polar and Cartesian coordinates are not identical, and we're going to look at 2 more examples here where you'll see that. So for the first one, we have 2 and then 2 pi over 3. So again, using these equations, we have for the x-coordinate 2 cosine of 2 pi over 3. And then the y-coordinate is 2 sine of 2 pi over 3. Now, if you take the cosine of 2 pi over 3, you're going to get a negative 1/2. 2 times negative 1/2 is going to give you a negative 1. And then sine of 2 pi over 3 is going to be the square root of 3 over 2. 2 times the square root of 3 over 2 is just the square root of 3. So the polar coordinate to 2 pi over 3 is equivalent to the Cartesian coordinate negative 1, the square root of 3. And then the last one, we have 2 and 7 pi over 3. And I'll do the same thing. The x-coordinate is going to be 2 cosine 7 pi over 3. And the y-coordinate is 2 sine of 7 pi over 3. Now for this one, it goes back to something I mentioned in the first video. Here we've got an angle that goes completely in a full rotation, and then it's going to basically come back upon itself. So I'll do it up here. So if we started here at 0, 2 pi gets us all the way back to the x-axis, and then 7 pi over 3, we now have a 30-degree angle here. So 7 pi over 3 is equivalent to just pi over 3. And that's supposed to be an equals, not a less than, but let me fix that. I don't want anyone to be confused. There we go. So you could think of this as 2 cosine pi over 3, 2 sine pi over 3. Either way, cosine 7 pi over 3 or cosine pi over 3 is going to be a half. So 2 times a half is just 1. Sine of 7 pi over 3, same thing as sine of pi over 3. It's the square root of 3 over 2. 2 times the square root of 3 over 2 is the square root of 3. So there are the 4 points as Cartesian coordinates. Now, for the second example, we're going to go backwards. We're going to be given, these points in Cartesian coordinates, and we want to find the polar coordinates. But there's a trick to this. We're given that theta is between 0 and 2 pi. So we're not going to have any negative values of theta, and we're not going to keep wrapping around. But it says that r is restricted to be less than or equal to 0. And in our case, that means we're going to have negative values of r. And just like the example over here, which is really not a very straight line, but when r is negative, it's on the flip side of the angle. We have to keep that in mind with these. So these ones we just are going to have to think a little bit as we work through the problem, and drawing pictures might be helpful. So the first one is the point 3, 3. So this is in Cartesian coordinates. We want to change it to polar coordinates. Now the point 3, 3, and I don't need anything super specific, but the point 3, 3 would be here. So in Cartesian coordinates, this is 3, 3. And I'm going to switch to a different color here for my polar coordinates. I need to find theta and I need to find r. I'm actually going to start out by finding theta here. I've got it slightly off my screen. There we go. Theta is found by taking the inverse tangent of y over x. So in this case, theta is the inverse tangent of 3 over 3. So we have the inverse tangent of 1, which means that theta is just pi over 4. So theta is going to be this angle here. But my r value is negative. Well, we'll get there in a second. Let me not jump ahead of myself too much. Let's find r. R is equal to the square root of x squared plus y squared. Since x is 3 and y is 3, r is going to be the square root of 9 plus 9. So r is equal to the square root of 18, or 3 times the square root of 2. Now, if r were positive, we would be done. We could say that our polar coordinate is the point 3 square root of 2 pi over 4. But we're given this crazy stipulation here that r has to be negative. So that means our r value cannot be this positive 3 square roots of 2, but rather it needs to be the negative of that. But we still need it to match up to this point here in red. So I need to have an R value that's down here that could then be flipped back up to this point. So my theta cannot be pi over 4, but rather my theta needs to add a whole other 180 degrees or a whole other pi to it. So theta is not just pi over 4, but it's going to be pi over 4 plus pi. So my theta would be 5 pi over 4. So with these, we just need to think about them a little bit to see exactly where we're going. So at negative 3 square root of 2, 5 pi over 4, I would go, starting here at the x-axis, I'd go all the way around to 5 pi over 4, and then that negative r value means I flip back up. So I'm going to hit that red point. So that would be the first one. Now, for our second one, we've got negative 1, 0. So in Cartesian coordinates, it's this point right here. So let's look at it as a polar coordinate. So theta is inverse tangent of y over x, so that's going to be 0 over negative 1. So we have inverse tangent of 0, so theta is 0. R is the square root of x squared plus y squared. Negative 1 squared is 1, 0 squared is 0. So we have r equals 1. Now, our r needs to be a negative value, so it's not going to be positive 1, it's going to be negative 1. And in this case, at the point negative 1, 0, okay, so here's our theta 0, r equals negative 1 is going to flip it back to where it needs to be, so we don't need to adjust theta at all here. So here we have the point negative 1, 0. So this one, they are identical. The third one, we have the Cartesian point, negative 1 square root of 3. So we're going to be up here, roughly. And we need to find theta and r one more time. So theta is going to equal the inverse tangent of the square root of 3 over negative 1. So theta would be the inverse tangent of negative square root of 3. And if you do this on a calculator, it's going to give you negative pi over 3. But remember, we are limited to theta values between 0 and 2 pi. Negative pi over 3 is this angle down here. If you just add 2 pi to it, you're going to get its equivalent to 5 pi over 3. So my theta angle is down here, and that's going to actually work for me. Because my theta angle, if I were drawing this perfectly to scale, it's going to line up with that point. The r value is the square root of x squared plus y squared. X squared is going to be 1, y squared is 3. 1 plus 3 is 4, so we have the square root of 4, so r is 2. Now, our r value has to be negative, and that actually is going to work in our favor here. Because if we're along this theta value of 5 pi over 3, with the r of negative 2, it's going to flip us back onto the point that we want. So once again, with these, it's very helpful to have a picture to imagine exactly what's happening. Now I've run myself out of space for the last one, so I think I'm actually going to try to do it on the top of this next page here. So for this last one, we're looking at 4, -3. And 4, -3 is going to be about here as a Cartesian point. And just like with the others, we want to find theta and then r. So in this case, theta is inverse tangent of -3/4. And this does not work out like the other ones do. This does not work out to anything nice. So I'm going to just leave it as it is. Now, let me really quickly draw this in. If you were on a calculator to punch in inverse tangent of -3/4, you're going to get a negative angle. And it would be this negative angle in here. So just keep that in mind for a second. We're going to have to do a little adjusting to this in a minute. Let's now find r. r is equal to the square root of x squared plus y squared. So that's going to be 16 plus 9. So r is equal to the square root of 25, or 5. Now, looking at this angle here, okay, which would be the inverse tangent of -3/4, and our r value of 5, it would give us our point right here. Great. The problem is that it doesn't match what we're asked to do. We're asked to find an angle between 0 and 2 pi and a negative r value. So what we're going to have to do is we're going to actually need to look on the other side of this. So r is going to be -5, so it's going to put me over here somewhere. And instead of it being this angle, I need to take it a full 180 degrees, which is pi radians. So our angle is just going to be inverse tangent of -3/4 plus pi. And it's not very pretty, but it's precise. And there we go.